Welcome to Starknet Fundamentals. My name is David Barreto and I'm a developer advocate from the Starknet Foundation. This session is a collaboration between the Starknet Foundation and OpenBuild. In this video, we will discuss four main topics. 1. Why Cairo? This section is the motivation behind the creation of the Cairo programming language and the unique features it brings to the table. You'll understand why Starknet has its own programming language instead of using Solidity. 2. Why Starknet? In this section, we will talk about what makes a Starknet unique among other layer 2s and how it solves Ethereum's scalability limitations. 3. Smart wallets. In this section, we will look at Starknet wallets and how they are more flexible and powerful than regular wallets or externally owned accounts. 4. Architecture 101. In this final section, we will look at all the different components of Starknet and how they interact with each other and with Ethereum. Let's get started. This is a very common confusion that I see with people about names. What's the difference between a Starknet or a Starkware and a StarkX? These things are related but not the same. So a Starkware is actually a company based in Israel that actually developed all the technology used by Starknet. The core of the engineering team building and evolving Starknet at this point in time is actually employees of Starkware. And the founder or Starkware and the current CEO is the mathematician that actually invented the Stark's CK proof that powers all this new innovation. It actually triggered all this new phase of zero knowledge rollups. So that is a Starkware. It is a company. Now, the first implementation of ZK Starks that a Starkware did was called a StarkX. And a StarkX is a permission system. So you cannot just go and use a StarkX directly. You will actually need to get into a contract agreement with Starkware to use it. And then StarkX has some fixed things that it can do. You can mint, you can trade tokens, you can do futures, synthetics. There are many apps that actually use StarkX that you might not even know about it. Like, for example, DYDX version 3 actually runs on a StarkX. RhinoFi, SoRare. Many apps actually use StarkX under the hood because that is the first thing developed by Starkware, and it's actually fine-tuned for these very specific use cases. So it's extremely high performance, extremely cheap as well. It's actually the place where Cairo actually was developed. Cairo was developed for StarkX initially as an internal tool to make it easier to increase the capabilities of the system. It was just after a while that Starknet decided, you know what, we actually evolved this technology so much that we want to create a system that uses the same technology, this same type of zero knowledge proofs, but actually now people can use Cairo on their own to create a smart contract and deploy them anytime they want without requiring any permission. So that's how Starknet was born. So Starknet is like a step forward from StarkX. So now it's as a permissionless system. It's a layer 2 rollup. So it uses Ethereum as a security layer. You can deploy your own logic through smart contracts without having to require any permission from a Starkware. Finally, we have the Starknet Foundation, which is an organization more recently created about a year ago. And it's a non-for-profit organization whose goal is to actually help grow the Starknet ecosystem by initiatives like this one, trying to onboard developers or have some partnership agreements with some builders to create some apps or to help with the decentralizing the governance of the system. So that is the goal of a Starknet Foundation, and that is the organization that I work for, say Manmeet, Gian, and Robert. So that's it. That's the different terms that you might heard in the space. Hopefully that helps to clarify what they mean. Our focus for today, obviously, is going to be Starknet. So why Cairo? And some of you actually, while we were waiting for the session to start, were asking me, why do you guys develop your own programming language? Why not just use Ethereum? So let me tell you why Cairo is important, even on its own, not even thinking about smart contracts, just Cairo as a general purpose programming language. I can explain that with an example. Imagine you're the head of a space exploration agency of a small country, and your goal is to send a spacecraft to Mars, okay? So you need to find ways to save fuel as much as you can to make the rocket as small as possible, to make it as cheap as possible. But you need to calculate two important things. You need to know when to launch the spacecraft and the trajectory of the spacecraft as well. Those two things are very complex to calculate, so you might have to go to your engineering team and say, hey, please create a program that actually find these two variables that we need. And they might decide to actually use a language that is high performance like Rust to create the program and find those answers. And after a while, they actually come back. Here we have the program. It's written in Rust. It's a very high performance. But the issue is that it is so complex, the computation, that you actually need a supercomputer to run the program to be finished in a reasonable amount of time. Because otherwise, in a regular computer, it could take a very long time. It is not feasible. And the issue is you don't have a supercomputer in your agency, not even in your country. The only way that you found to execute this program is because a rival country has decided to let you use their supercomputer to run your program, right? And say, okay, well, it's a rival country, but you don't have any options. So what do? Say, sure, let's actually work together. I'm gonna give you the code, right? You're gonna run it for me. And then when you have the answer, just give it to me, right? So they give you the result after some times, but then you have an issue, right? Like when you get the result, how do you know if the supercomputer maybe didn't malfunction while executing your program? Maybe one bit flipped. It actually can happen. And, a small change in the result happened as a result of this malfunctioning. But also, how do you know if the rival spy agency didn't sabotage the result just to, sabotage your whole program? It could, even a small change can derail the whole space exploration program. The thing is, with a language like Rust, with C++, JavaScript, you can't trust the results. You don't know if it was executed correctly. The only way for you to know if the result is correct is basically to ask another country that has a supercomputer to run the program and compare results. And to do that multiple times, right, to avoid for collusion. And then say, okay, if enough supercomputers to give me the same result, I can trust it. But it's very inefficient. It's very expensive as well. So just with a one single party, you just can't trust the result. You don't know if it's true or not. The thing is, if we go back in time, and let's say that your engineers, instead of using Rust, they actually use Cairo, which as you're going to see, the syntax is very similar. Now, when you give them the program to execute, the rival country will have to run the Cairo code in the Cairo VM, and they're going to give you back the result as before, but now they're going to give you a cryptographic proof of the execution, right? And this cryptographic proof, now you can run it through your own computer. You can verify it on your own computer. And if the proof is valid, then you have guarantee, almost 100% guarantee that, no one tampered with the execution and that the system didn't malfunction. Because if it did, the proof will be invalid and there's no way for the rival country to forge a fake proof. It's going to trick you into accepting a wrong result. So in other words, now you get the superpower that you and your regular computer, your laptop, your smartphone, is actually able to keep a supercomputer honest. Because if they cheat or if it malfunction, you will know it right away. And that's only possible with a language like Cairo, which is part of a new breed of programming languages. So far, the only one that I know that has those properties. That is a high-level language, of course. And now it's very easy to use. I'll give you another example, maybe in a different field. Let's talk about machine learning. Let's say your boss, you're the engineer, your boss comes to you and say, you know what, it would be great to have our own AI model trained with our own data to have an edge over our competitors because we have a lot of data that we don't want to make public. So we're going to use ChatGPT, we cannot train it with a public, but we want to create a model that is internal to be used by only our employees. And you think, well, you know what? It is possible because there are some good open source models that you could use, like Llama 3 just came out recently. But again, the issue is that you still have to fine tune and keep training that model with your own internal data, which could be a lot of data. And that requires a lot of computing power that you might not have in your company. So what you do, well, basically you hire a third-party company, let's call it Company B, and you tell them, hey, I'm going to give you the private data of my company. I'm going to tell you which model to use, and you're going to train it for me. Maybe Company B uses something like Python. That's what I imagine people use to train models. I don't know. And after a while, they give you back the model now trained with your data. But you have the same issues before, right? Like, how do you know if this model, this new ChatGPT is actually trained with all your private data, right? You really don't know. And how do you know they actually use the model that you wanted to use? It is possible that Company B actually cut corners just to save cost and make a bigger profit. But you have no way of knowing if that's the case. But if you repeat the experiment with Cairo, now when they train you the model, they also give you the cryptographic proof of the execution. So you will know it almost with 100% certainty. That model that you're getting has been trained with all your private data and using the exact model that you request them to use. They didn't cut corners because if they did, the proof will be invalid. It is almost impossible for Company B to forge that cryptographic proof. So again, that is a superpower of a language like Cairo. So to summarize some of Cairo's features, first of all, it creates provable programs that you can prove the execution, so computational integrity. It runs on top of the Cairo virtual machine, so we don't use the Ethereum virtual machine, and basically because the Cairo VM is fine-tuned for ZK proof, while the Ethereum virtual machine is a traditional computer architecture, actually. The syntax is inspired by Rust. It is not exactly the same. It's very similar, but not the same. It has a similar ownership model. If you ever know Rust, you know what it means. That also allows for high performance execution. It is a strongly typed system like Rust. It uses traits instead of an inheritance like Rust, and it uses macros for meta programming. So if you have never used Rust in the past, then you're going to learn how the different type of programming language actually looks like. And Rust is very popular because of its syntax, because of its power, because of its performance. Cairo, that's why we chose Cairo to actually take some of those syntax from Rust, implement it into a language. It can be used outside of Starknet. So I gave you two examples on when would you use or what could you use those things out of the blockchain like a Starknet. But the main use case right now is obviously to create smart contracts for a Starknet. But the best part for me is that it takes advantage of zero knowledge proof. But compared to Circum, you don't need to know anything about how ZK works. It abstracts away everything for you. So it makes it much more accessible than alternatives. Even more accessible than what Cairo used to be like 2 years ago. 2 years ago, Cairo was a very low-level language, very hard to pick up. The language that is today is actually very much high level, so you just can focus on the logic of your app and kind of forget about the whole ZK connection and circuits behind it. All right, so just to give you an idea of how Cairo looks like and how similar it is to Rust, this is an example of how do you create a custom data type with a struct. In this case, the custom data type is called rectangle. It has two fields, height and width. Just like Rust, it is a strongly typed language. You have to define the types of these fields. In this case, in Cairo, it's an unsigned integer of 64 bits. You have unsigned integer of 8, 16, 32, 64, 128, 256. These built-in types are called scalar types. So again, it's just for giving an idea how Cairo looks like. We're just not going to do a deep dive today. We have a session dedicated for Cairo, session 3, but I might as well just have an idea how it works, how it looks like. This is how you create a reusable, let's say, functionality with a trait, very similar to Rust. In this case, I will create a trait called shape geometry, which has two methods. In this case, you only define the signature, just like Rust. There's an important difference. In Rust, you don't have to define the type of self, right? In Cairo, you have to, okay? That's one different. So this is an example of why Cairo it borrows a lot from Rust, but it's not exactly Rust. So there are some differences that you need to be aware of. When you want to implement this trait, actually define the body of those two methods, you actually create an implementation. But again, different from Rust, in Cairo, implementations have names, like in this case. So the syntax is a bit different, right? In Rust, you will see a for here, and here you see an of. If you don't know Rust, that's okay. Just keep in mind there are some small differences, but you can define implementation, basically take the trait with the signature and implement the logic behind each of these. So this is how Cairo looks like, and hopefully it gives you an idea that it's actually a high-level language, very flexible, strongly typed, very similar to Rust, not exactly the same. So again, just to give you a sneak peek of now how Cairo looks like in the context of a smart contract for a Starknet. So let me show you here. So when you want to create a smart contract on Starknet, you define actually a module. Because in just vanilla Cairo, let's say Cairo not for a Starknet, a module is just for, just to group functionality. To tell the compiler that this module is actually a smart contract, you need to use an attribute, the Starknet contract. And this type of programming is called actually meta programming because attributes are macros, and macros, what they use, they actually consume the code that you define under the macro and transform the code. In this case, the transformation is to turn the module into a smart contract. So that is meta programming. It's popularized with Rust, also used in Cairo, just with different macros or different attributes. When you want to define the storage of a smart contract, you actually define a struct that it has to be called storage. Maybe that will change in the future. You can define different names, but right now it has to be called storage. And then as fields, you define, okay, what do you want to store in your smart contract? And that struct has to be annotated with the attribute storage as well. Again, because meta programming. If you want to define let's say like the public or the things that your smart contract can do, you actually use a trait to define the interface of the smart contract. This trait is actually accept a generic type. In this call, just call it T contract state, but it could be called anything, it could be called just T, which we define the signature of the method that a smart contract is going to support. This is similar to Rust, but again, I mentioned that you have to define the type for self in this case. And notice that there's two ways to do that. So when you have a method that actually that is going to modify the internal state of a smart contract, you need to pass the smart contract state, which is the type here, or the self parameter, as a reference, so you can modify it. But if you only want to read from a state and you don't want to modify it, actually you want to prevent from the state being modified, you can actually request the state to be passed as a snapshot, which is like a read-only version of a complex object. So now when you actually want to implement the logic of that trait or that interface, you define a name implementation that is actually extending from this trait that we define here. And you have to annotate that with a special attribute called ABI embed v0, basically saying, hey, this implementation is actually going to be the ABI of my smart contract. So the public interface of the smart contract that anyone can call. So you can see that I have to implement the signature that I defined the trait, the get and the set exactly as it was defined, but now I have to define what actually it does when you call it. So you can see here how I actually write data to the store, to the storage. You can see the store data is one of the fields defined in the storage. And I can use the method write to write data to it. But if I only want to read, then you access the same field from self, and then you just call the method read. And that's a very simple example of how you write and read from storage and define the public interface of a smart contract. Again, this is just like a crash course into how it looks like. We have a dedicated session for a smart contract, session 4. We're going to go into detail there. I just want to give you an idea of how a smart contract on Starknet actually looks like, because if you know Solidity, it's useful to have a comparison early on. So, okay, to summarize this session, why Cairo? Because it creates provable programs. It gives you the proof of the computational integrity, that no one tampered with the execution or nothing failed when it executed. You can verify without re-executing, right? And you think about the example of the space exploration. One way was to just have multiple supercomputers and compare the results. That's actually how Ethereum works. But with Cairo, you can just verify that the result is correct without having to re-execute the program. It is a powerful and flexible language, in part because it's a high-level language. It abstracts away all the complexity of ZK, and it borrows a lot of syntax from Rust. It prevents cheating and malfunction. In the case I mentioned that it actually keeps a supercomputer honest thanks to the ZK proof, and that's one of the superpowers. And that's actually how we achieve scaling on top of Starknet, which is the next session. You're going to see why Cairo is important in the context of a blockchain. We talk about why Cairo, so let's now move on to Starknet. So let's talk about the L1 scaling problem, right? Basically talking about how Ethereum works today. So in Ethereum, you have a machine that selected randomly once in a time to actually produce a new block. Let's call it the block producer. This is a validator that it has the chance to produce a block. This block producer is going to take transactions. It's going to create a new block. And it's going to tell the world, hey, if I execute all these transactions in this block, I actually get this new global state of the Ethereum network. Let's say for simplification that the new state is 42, right? So it tells the world, this is the new state if you execute all the transactions in the block. But of course, in the case of Ethereum, all the other validators, they don't take the word for it. They're not going to trust the block producer that is being honest. What they do is actually take the block that the block producer is creating. They're going to take all the transactions in the block. It's going to execute all the transactions in the block. And it's going to verify that they actually get to the same final state, the same 42. So that's the way how the validators keep the block producer honest and the system in a safe state. Because all these machines are doing the same job independently, just to verify that they get to the same result. That's part of the consensus protocol, which is very robust, right? You keep anyone from cheating as long as at least half of the network is honest. But the downside is that it's very inefficient, because even a simple block with a small transaction actually has to be re-executed thousands or maybe 10,000s of times in different machines around the world independently just to compare results. So you can see how it's robust but inefficient. In the case of Starknet, When a Starknet proposes a new block, in this case, it's not going to be a block for layer 1, it's going to be a block for layer 2. It's also going to create, the block, it's going to execute the transaction. It's going to say, hey, the new state of the network, in this case, a Starknet, is 42. But now it's also going to give you the cryptographic proof of this execution, right? Because it's using Cairo under the hood. So now the validators, in this case on Ethereum, because Starknet sends the proof to Ethereum, now the validators, they don't have to execute all the transactions in the block just to verify that it's 42. They only have to verify the CK proof, because if they do and it's valid, then they will have certainty that the new state is actually 42. So all the validators on Ethereum, they only have to verify the proof, and that verification is only a fraction of the effort of actually executing all the transactions in the block that Starknet is proposing. So you can see here visually how you gain a lot in performance when you think of a system as a whole. Of course, there's a little payoff here, a trade-off, because now Starknet not only has to execute the transactions, it also has to create the cryptographic proof associated with that computation, which takes additional computing power. But you only pay that price once, and you have the savings everywhere. So as I like to say, you execute only once, and then you verify everywhere. You don't execute everywhere. So this is how we actually are able to handle way more transactions per second with the same level of security as Ethereum, but without in a much cheaper way, because the bulk of the work is done by a single computer on a Starknet, and the cost done by the Ethereum network is actually just a fraction of it. So I mentioned that it's cheaper to verify compared to execute, but how cheap? If the number of steps that the sequencer, or in this case a Starknet, has to do to execute the transaction or execute all the transactions in a block, the effort done by the Ethereum validators to have certainty of this new state is only log square of x, or just polylogarithmic, right? So x is the effort of the sequencer, and just polylogarithmic the verification on Ethereum. So if you put it on a chart, it's easier to see where the gains actually come from, because the bigger the block on a Starknet is, the more transactions are executed. The log square of x grows at a much slower pace than the actually underlying computations. So the bigger this gap is, the more you're gaining performance, getting the same level of security. And this is just only the base example of validity proof, because actually in session 2, we're going to talk about proof recursion, which makes this distance or these performance gains actually much wider using a technique that we're going to discuss tomorrow. But just, out of the bat, that's how much you gain just by using Cairo or using the Starknet and validity proof. You can actually go, there's a link here for Wolfram Alpha if you want to see the functions, and you just play with it and just increase this number, for example. So for me, a rule of thumb to think about this technology used by Starknet is that validity proof is to computation what the zip algorithm is to file size. It's a type of compression. Just validity proof, it creates compression of computation, while zip creates computation of file size. Now, what is this validity proof, right, used by Starknet? So it's a use case of zero knowledge proof. As mentioned, you can use CK proof for privacy, or you can use it for scaling. We decided to use it for the latter. So it convinces the verifier on L1 of a new L2 state without sharing transaction details. Okay, we only have to send the validity proof. We don't have to send all the details of the transaction that happened on layer 2 for it to be verified on layer 1. So the amount of data that we send to layer 1 is much more smaller than compared, for example, optimistic rollups, that they actually have to send the details of all the transactions that happen on layer 2. That's what I'm saying, that optimistic rollup, we're going to have a hard time competing in performance against ZK rollups like Starknet, because by definition, they have to send all these transaction details for an external entity to keep an eye that no one is cheating and submit a fraud proof. The fact that we don't share transaction details from L2, or that they are not needed to verify the cryptographic proof, doesn't make a Starknet or the transactions on a Starknet private. Starknet was never built, at least not right now, for privacy. It's only meant for scaling. So some details are actually leaked, and we don't mind, because the goal of Starknet is not about, right now, privacy, it's about performance. But what it does is that it makes verification very efficient, very succinct. Now, because in our system we use validity proof, we like to call Starknet to be a validity rollup. I know it's common to call CK rollup, this type of rollups, but we like to term validity rollup because of the connection with validity proof. And because ZK rollup has a strong implication about privacy, which is not the case. The underlying system for proving is based on Starks, not snarks. If you know anything about these two, that makes sense. I'm going to explain a little bit later. But just make sure, Oli Ben Sasson, the CEO of the company of Starkware, is actually the inventor of CK Starks. And as you know, Starks are being used on different protocols. I think Polygon is also using Starks, so they're borrowing technology developed by Starkware to power their own CK EVM. They have efficient proving and verification, and that is one of the superpowers of Starks. The proving part is very efficient. So let's compare a bit more Stark versus Stark. This is a very high-level comparison because there are different. These are like two families, right? But within those families, you have implementation, especially in the case of Snarks. But at a very high level, the main differences are that the verification of the CK Stark or a validity proof created with Starks is polylogarithmic, right? As I mentioned before, the two charts that I showed. In the case of a Snark, it's actually constant. So it doesn't depend on the complexity of the underlying computation. Now, the proof size, the validity proof that we actually send from layer 2 to layer 1 for verification, in the case of a Stark, the Starks is actually about 400 kilobytes. And in the case of a Snark, it's actually much smaller. It's almost like 300 bytes, right? So there's a couple of orders of magnitude difference here. So just seeing these two properties, you will say, well, the Snarks looks like a much better deal than Stark. Why did we bother to use Starks at all? And the reason is here. The proving with the Stark is much more efficient than with the Snark. No one talks too much about that because the proving system right now are all centralized. So it's very easy for all companies to hide the issue with the performance of proving, but eventually they're going to become a bottleneck. So we're trying to have a system that's going to withstand the test of time and it's going to be able to evolve as much or way more than our competitors. Another advantage is that Starks, they don't require any trusted setup to work, while any system based on Snark, they will. And this trusted setup is basically come up with some secure or some password secure set of numbers that the prover and the verifier will have to know. But if that secret is leaked, the whole system gets compromised. So with a Snark, you don't have that issue. There's no trusted setup because every time you use a Snark, you have to be mindful of how they actually seeded the system with this secret. Because if they do it incorrectly, the whole system is compromised. Another advantage of Starks is that they're still deemed to be quantum secure, meaning that if a quantum computer sufficiently powerful comes online that is able to break encryption, like elliptic curves of stuff like that, CK Starks are still deemed to be secure, unbreakable. While Snarks, because they make use of these cryptographic primitives, they're actually going to be broken. So again, thinking long-term, the security of a Starknet is a priority. So that's why Stark, we actually give a premium to these properties, even at the downside of a bigger proof size and a slightly more complex verification time. I mentioned that Starknet uses the Cairo virtual machine, and we don't use the Ethereum virtual machine. And that is for a simple reason. Any CK rollup that tries to use the EVM, well, they try to maximize compatibility with existing smart contracts, but they sacrifice performance. The idea with the Cairo VM is that we want to get the max performance possible, even at the cost of sacrificing compatibility. The fact that you cannot deploy a Solidity smart contract to Starknet, you have to rewrite it basically to Cairo and use it. It's much more work. We had to develop our own tooling, not only our own language, but our own testing framework, our own everything from scratch. We cannot use the same tools that you use in Solidity. But we're thinking long term. If we want to get the max performance of this system, we need to have a stack that is custom made for this new paradigm of CK proof or validity proof. The EVM was never meant to be used in this context of this type of new architecture. So there's a lot of conversion of friction happening in the middle to allow for this compatibility that eventually is going to have some performance bottlenecks. Vitalik had a blog post some time ago talking about the different types of EVMs or how will they classify it. And he actually came up with 4 categories for EVMs or for CK EVMs, no? CK rollups trying to use the EVM as their baseline. So the type 1 CK EVM, the idea is that you could deploy any smart contract that you have on a layer 1, on a layer 2 without having to do any change. And that's like a unicorn, right? Because the issue is that if you do that, and because the EVM was never meant to be used in this new paradigm, it will be very slow to create the cryptographic proof associated with the computation. So no one is actually doing that right now. It's very hard, and it's dubious is worth it because of the trade-off in performance. Then you have the type 2 CK EVM, where compatibility is very high, but it still is not 100%. There are going to be some changes on how storage, the data structure of storage is actually handled. But again, performance is not great. It's very low. So no one really working on this area today. Then you go to a type 3 CK EVM. Now the compatibility still, let's call it partial, because now the number of changes start to increase. Different storage data structure, different hashes, different precompiles. You get a faster performance now compared to these two options. And actually, you see now different projects working on this type of CK EVM. You have zkSync, you have Scroll, Polygon CK EVM, but you also have Kakarot. And Kakarot is interesting because it is a CK EVM on borrowing a lot of the infrastructure from Starknet. So you're able to deploy Solidity smart contract, but under the hood is actually executing Cairo bytecode. So you get the best of both worlds. You can check out that project. You go to Starknet Kakarot. I don't think they're in mainnet right now, but this is to be very close to launching. It's an interesting project if you want to take a look. I'm going to put it here in the chat, and I'm going to put it on the Discord, Kakarot. So again, the idea of Kakarot is having an EVM powered by the Cairo VM, but the idea is that it's like a bytecode transpiler, if that makes any sense. Keep an eye on it if you want to do that kind of deployment. But finally, you have the Type 4 CK EVM, and the Type 4 CK EVM basically means that it is a completely different virtual machine, nothing to do with the Ethereum virtual machine. So you have no compatibility. You have to rewrite your smart contract into a new language that compiles to a new virtual machine, which is, an extra hurdle. But what you get is a very fast performance, especially for the proof creation. And that's where the Starknet lives with Cairo. Also, Polygon has also a project called Polygon Mining, trying to do the same. And then you have Aztec. Aztec is a bit different because they actually try to go for privacy. So that might have different trade-offs that I don't want to compare here. But they fall into this category of being a completely different virtual machine. So this is where Starknet is in this classification, and also Kakarot, an interesting project using Starknet tech stack. Now, talking about finality or layer one finality, we know that Ethereum finality is achieved pretty much every 6 minutes or so. In the case of optimistic rollups, finality for layer one, basically when you're able to withdraw your funds from layer two to layer one, it's actually taking about a week. Right? So think about that. You need to withdraw assets. You have to wait a week to be able to use it on layer one. In the case of Starknet, it's actually 2 hours, the time you have to wait, because that's how frequently we send validity proof from layer 2 to layer 1. And once the proof is verified, then you can just move the funds to layer 1. Now, this is finality for layer 1, but finality in layer 2 directly is very short. It's about 3 seconds right now. So it's verified to get confirmation of transactions. It's only when you want to withdraw assets back to layer 1 that you have to wait 2 hours, although there are systems to speed up this with some economics, but the baseline is 2 hours. So you can see that it's a big benefit compared to optimistic rollups when it comes to withdrawals or selling. Some statistics about the performance of Starknet. We actually have 2 main block explorers. One of them is called StarkScan. The other one's called Voyager. And we have, for example, a peak of 47 transactions per second, which might not look like much, but keep in mind that on a Starknet, something we're going to discuss later, every transaction is actually multiple transactions bundled into a single transaction. That's one of the benefits of account abstraction. So much better is to compare user operations per second. And one of the peaks that we saw is 238 UOPS. This number is actually closer or more comparable to a transaction that you will see on Ethereum, right? So this is how much Ethereum or Starknet is able to handle on peaks. If you want to see it by yourself, you can just go to StarkScan. I'm gonna put the link in the chat and on Discord. StarkScan. Because in here, you can go to TPS speed. You can see the data here, right? So if you can see some of the peaks that we get when it comes to just raw TPS. But user operations per second might be more meaningful. And you can see some data here, right? 3 months. Yeah, so some of the peaks I was showing before. So we're able to handle much more traffic than Ethereum, thanks to all these characteristics I've been talking about so far. So to summarize this section of why Starknet. So first of all, the whole tech stack is optimized for zero knowledge proof, or what we call it validity proof, which gives you more computing power and you pay much less in gas fees. Actually, right now, transactions on the Starknet is sub-cent. So imagine how much you can do with just these very low fees. And with the security given by the ZK proof based on the Starks, and verify on Ethereum, the most decentralized layer 1 blockchain there is. It's a very powerful programming language in Cairo, and the tech stack is actually pretty battle tested because it's been used for a long time. Remember that this technology was first used on Starknet, and Starknet has been used for major applications. So in the time that's been used, more like $1 trillion of transactions have been secured by the same tech stack of Starks and validity proof. Withdrawing assets from layer 1 to layer 2 is about 2 hours. That's how fast we do the settlement. And there's no need for trusted setup. So less risk of the system being hacked compared to system based on snarks. Smart wallets. This is a topic that really like. One of the reasons that I actually got very excited about Starknet when I started working at the foundation and also at Starkware even before, is because of all the advantages in security and UX, which I think are crucial for the adoption of Web3 technologies. So a smart wallet is different from a regular blockchain wallet in the sense that it allows you for more features. So for example, you can sign transactions using Touch ID or Face ID, which give you a higher level of security. You can execute multiple operations in a single transaction. So an example of this could be if you go to, I think it's Akubo, one of the DeFi projects on Starknet, you can rebalance your whole LP liquidity when it goes out of range in a single click, in a single transaction. It does all the, buy the tokens of the trade, set up the new boundaries for the LP, and activate that all in a single transaction. Or for example, no longer you need to do first approve the use of tokens, trade, and then remove the approval. It does all of that in a single transaction. So you only sign transaction once. It allows also for the paymaster, which Avenue has available. If someone can help me share those links on Discord of Kubo and Avenue, if you want to explore some of these features, that's a place to do it. And this is all possible because of a thing called a account abstraction, right? And account abstraction is the thing that enable smart wallets. And on Starknet, every single wallet is a smart wallet. This is in clear contrast to Ethereum, where you have externally owned accounts and you have smart contract wallets like multisigs, and you have wallets with account abstraction. You have 3 types of wallets, all with different features. On Starknet, they're all based on account abstraction. They're all smart wallets, which makes it easier to implement better UX supported by all the applications in the ecosystem. There are 2 main providers for wallets on Starknet. One is called Argent. The other one is called Bravos. They are great both, so you can just pick whatever you like the most. The links are there. I was talking about this thing that you can do complex interactions in a single transaction, right? So sometimes an action requires multiple steps or multiple user operations. The typical example will be that if you're going to do like a trade on something like Uniswap, or in this case, Kubo on a Starknet, normally in Uniswap, you will have to first approve the use of the tokens by the protocol, and then you will do the trade. So that will be like 2 different transactions, no, typically. But we know that those 2 transactions, they're actually just 2 steps in a single process. So what will happen on Ethereum is that you might think that because you sign 2 transactions one after the other, they're going to be included in the single block in the same order that you define them. But it's actually not the case. You don't have control of how these transactions are included in the block. Maybe you can define the order is defined by the nonce, but you don't have certainty they're going to happen right one after the other. It could happen that, the transaction for step 1, they both happen in the same block, but maybe some transactions get included in the middle. Or it could happen they actually get included in 2 different blocks, right? You don't have control over that. Because of that, someone can actually put a transaction in the middle of your transaction in a way that actually can be harmful to you. And this was called the MEV, the maximal extracted value. And I put here an example of flashbots because it's a very well-known protocol on Ethereum. So the fact that you don't control, or that the gaps can be included in operations that belong to the same action, opens the door for this type of economic attack, MEV. But now, when you have something like multi-call on a Starknet that you can include multiple user operations in a single transaction, let's call it a bundle, now you have certainty that those transactions, first of all, they're going to be included in the same block. They're going to happen one after the other. No transaction can get in the middle. So that way you can prevent some types of MEV attack, at least the sandwich attack. You cannot prevent front running, unfortunately, although right now it doesn't really happen because we only have a single sequencer, so it's controlled by Starkware. So it will mean that if anyone can extract MEV, it will be a Starkware, which they don't. But when it gets decentralized, front running will be possible, but not including transactions in the middle, but also you have the guarantee that the things are executed in the sequence that you define in the same block and only signing one single transaction. So there's a big win in usability. Now, I did mention account abstraction as the baseline for this smart wallet, but what account abstraction does under the hood is just decoupling of the signer from the account. And the signer being the device that signs your transaction, could be your phone, could be your laptop, and is identified by a private key, okay? In the case of Starknet, usually this private key could be actually stored in the secure enclave in your system. We're gonna see it later. Then you have the account, and the account is a smart contract on a Starknet, and it's the thing that holds the assets and verifies the signature, right? So it's also the thing that executes transactions using multiple. So you can see that every account on a Starknet has an associated smart contract deployed that only reacts to your signer, right? So only your signer can send transaction because the account has some logic to verify that the transaction is only signed by your device, for example. But now the owner of the assets is the account, and now you can have much more advanced logic on how signature verification happens, how execution happens, which allows all these things like multi-call and more advanced use cases. Now, account abstraction in practice at a very high level, I mentioned that if you have, for example, a wallet installed on your phone, browser, agent, so your phone will be the signer, right? So when you want to execute a transaction or make a call of a transaction on Starknet, what's going to happen is that you, first of all, you're going to have a smart contract called the account contract deployed in Starknet that is connected or related to your signer. This is the public interface that smart contract will have, defined by the SNP6, similar to an EIP, but in the case of Starknet. It has the execute, the validate, and its valid signature. We're not going to go deeper into account abstraction in Basecamp, but I can give you access to a workshop that actually touches on that, and on Node Guardians there's also a quest to learn more about how it works. So if you want to interact with this target smart contract, what's going to happen is that you're going to send a transaction. Your signer is going to send a transaction to your account contract. Your account contract is valid, is going to verify the signature of this transaction using the validate. And if it's valid, it's going to move on to the execution part and actually going to call the target contract. So at the end of the day, is your account contract the one actually calling the target contract just by request of the signer. So it's a bit different how it works because you have this decoupling compared to externally owned accounts. Now, signature verification, as I mentioned, it is a function that you can program anywhere you want. And because it's programmer, you can do things more advanced. For example, you can have a single signer, which is the default case when you have browser or agent. You can also have multiple signers, like a multi-sig, but more like a native multi-sig that is supported by all the applications. Compare that to Ethereum, when you have a multi-sig like Safe, some apps actually, they don't support sending transactions through a Safe, right? The account contracts or wallets based on smart contracts are a second-class citizen on the Ethereum ecosystem compared to externally owned accounts. In the case of a Starknet, they're all the same type of wallet. It's just configured different, so they're all first-class citizens. You can do things like the hardware signer. When you use your Face ID or Touch ID, you're actually making use of the secure system of your phone or your laptop. Then you can think like a social recovery. Like if you lose access to your wallet, you can define like friends or family that can help you recover that keys, doing some kind of off-chain verification. You can have session keys that are big for gaming, so you don't have to sign every single transaction. You just give a key with limited permissions to a game client, so it can sign transactions for you for a limited amount of time, for a limited amount of assets, and just for a particular type of assets. And then you can also support multiple elliptic curves. You can support the stack-friendly curve, you can support the Ethereum elliptic curve, or you can support the standard elliptic curve. So they can give you more flexibility of how this signature or what the signer can be. Now, when you combine account abstraction with a secure enclave, it will turn your smartphone into almost like a hardware wallet. Because if you see any smartphone, there are actually two systems in it. You have just the shared system with all the apps run, they share the memory and the CPU. But then you have also a smaller system that is actually a secure enclave. That's the name that iPhone uses, but has different name for different vendors. That is fully optimized for things like a random number generation, crypto keys management, signing with hardware. That's the thing that Keychain, Touch ID, or Face ID actually use. So it has a dedicated processor, a dedicated memory just for this cryptographic of high security operations. And now with the account abstraction, you can actually have access to this system for sending transactions. Because Ethereum, for example, wallets can only use the shared system. It is mostly because of the type of elliptic curve signature that is supported on Ethereum. It's not the same supported by the industry as a whole, which is this particular curve, the SecP256R1. Secure Enclave is the name for Apple devices, but for Google, you have Titan M, does the same thing. For Samsung, you have Knox. And for any ARM device, you have the Trust Zone as well. And it also applies for laptops. So again, it's a much higher degree of security that you get when you enable a hardware signer on your wallet. And you're going to see that when you install Bravos or Argent, you have that option to enable a hardware signer. So in summary, the benefits of smart wallets are that you get better UX than regular wallets. You get things like multi-call, hardware signers, social recovery, session keys. All this is enabled by this account abstraction model, which is the decoupling of the signer from the account. And an account is a smart contract with a specific interface. This is NIP6. So every time you create an account, you have your signer and you have an account contract on a Starknet. It supports signing transactions with different elliptic curves. As I mentioned, could be Ethereum, could be the standard, or could be the Stark friendly. And on a Starknet, every single wallet is a smart wallet. There are no externally owned accounts today, which is a benefit in case of support of applications. This section is about the architecture. It's only like a very high-level overview of the architecture. So let's start with Cairo. You know it's a provable programming language, right? You know the syntax similar to Rust. What you don't know maybe is that Cairo doesn't directly compile to the Cairo VM bytecode. It actually compiles first to an intermediate language called Sierra. And Sierra stands for safe intermediate representation. And then from Sierra, we can compile to what's called a safe Cairo assembly. Cairo assembly is just the bytecode for the Cairo VM. This compilation is done by the sequencer. So when you deploy a smart contract, or in this case, when you declare it, that's when it does the compilation. The goal of Sierra and safe CASM is that without Sierra, in an issue we had before, is that it was impossible to handle reverted transactions, right? A transaction that when it fails, that you can handle it gracefully in a way that you can include it in the CK proof, right? So Sierra takes care of that even if a transaction fails, it makes sure that it fails in a way that is compatible with the proving system. And that's what we call safe CASM. If we didn't do that, it means that we will have a hole for denial of service attack. Another benefit of Sierra is that it also allows for the Cairo VM and its bytecode to evolve independently from how the language, the Cairo itself, evolves. So now we can make changes to both ends. We don't necessarily have to modify the whole thing because now we have this abstraction layer in the middle with Sierra. Now, to talk about the architecture, let's go back to the main story about why Cairo, right? When I mentioned about the space exploration, they just send in the program, they execute, and they go back to you with the result and the proof if you use Cairo, and you can verify the proof. Now, let's take a look at the modules of this example. And this is just an approximation of how Starknet works before we go to how it actually works. So it all starts with your laptop in your country, and that's when you have the Cairo program. First step, you will have to compile it to Sierra, this intermediate language. And that Sierra is what you actually send to the supercomputer of the rival country, right? So now the supercomputer, what they do is that now they have to compile that Sierra to save Cairo assembly or the bytecode for the Cairo VM. And now with that bytecode, they actually can run it in the Cairo virtual machine. And as part of the run, a trace is generated, and that trace is given to another module called the prover, who's actually the one in charge of creating the cryptographic proof of the execution. And that validity proof is the one that is sent back to you, to your computer, where you run your own verifier. And this is an example of, the space exploration. It's not exactly how Starknet works, but it's very similar modules. So you just want to do like an evolution of this towards the real deal. The output of the prover is not only the validity proof, it's also the result of the computation, right? So you get both at the same time. Now, in the case of actually Starknet, it all starts similar, that you have your computer or your smartphone. And again, this is an evolution of how it will actually work. So you will have to first, let's say you create a smart contract, you compile it to Sierra, then you send the Sierra code to, in this case, the sequencer, which is one of the nodes of the Starknet. The sequencer is the one that actually does the compilation to Cairo assembly or safe CASM. It will run it as a transaction in the Cairo VM. Then there's another machine, let's say the prover, or let's say it's called Sharp. And Sharp stands for the shared prover because it's the big machine that is only purpose is to create proof out of traces of the Cairo VM execution, not only for a Starknet, but also for all the StarkX apps as well. That's why it's called shared. It's shared with the StarkX. Now, the prover is the one who generates the validity proof, and it's sent as a transaction to Ethereum, and it sends to a smart contract written in Solidity called a verifier, and you'll get the result as well out of the prover. But again, this is just an oversimplification of how the system works. We're going to go into more detail tomorrow, but it's close enough to how it actually works. Now, why is it oversimplified? First of all, because Starknet uses smart contracts and not just plain Cairo. And because before you can execute a smart contract, you need to do two things. You need to declare the code. That is something new that you don't do in Ethereum, for example. And then you have to deploy it from the declared code. So two steps. Declaration is only for new code. If the code has been declared before, for example, in an ERC20 smart contract, you don't have to redeclare it. You can just deploy an instance of the same declared code. Now, the way you interact with the Starknet is via transactions, same as with Ethereum. And transactions must be signed. That's where the signer comes into play as well. So I mentioned that before you can execute a program, you have to declare it and then you have to deploy it. So let's talk about declaring a smart contract. Let's say that you write your smart contract with Cairo, a smart contract for a Starknet. You will compile it to Sierra on your computer, but then you have to create a transaction, right? Because you want to declare it on Starknet. And you do the transaction, or you create it and you sign it with your wallet. Now, the wallet will send a declared transaction to Starknet, and this is the Sierra code of your smart contract. It will go to the sequencer to go to the mempool. That's where all the transactions go first. They get collected. And then eventually the sequencer will compile your code from Sierra to the Cairo assembly. And the thing is, well, what do we send to the prover? Is it possible to prove the compilation of the smart contract? And the thing is not really, because to prove the compilation, it means that the Cairo compiler has to be written in Cairo itself, which is not the case right now. The Cairo compiler is written in Rust. So there's a mismatch here, right? How do you know that what the sequencer is doing, that the compiled version of your program is actually really the compiled version of your program, right? The sequencer could be cheating. How do you detect that without the proving? Because the Cairo compiler is not written in Cairo, it's written in Rust. So the compilation can be proven as of today. So the long-term solution for this problem is to write a Cairo compiler in Cairo, and that will happen eventually. So the compilation can be proven, right? So we close the issue that we have no way to know if the compilation is true or not. Now, the solution we have right now, which is like a stopgap solution, is like when you declare a smart contract, you also have to provide the hash of the Cairo assembly, the hash of the bytecode. So you let the sequencer to do the compilation from Sierra to Cairo, but now because you provide the hash of the Cairo VM code as part of the transaction, it's easy to compare if the hashes of the programs are the same. Because if they're not, you know that the sequencer is cheating, right? So that is a way that we prevent the sequencer from cheating, just by sending this hash of the compiled version of the smart contract in the Cairo assembly. I know it seems like a mouthful. This is normally done under the hood by the tooling, but just to keep an eye that the Cairo compiler is not written in Cairo, so compilation cannot be proven. So we need to have some solution in the meantime. So what it will happen in reality when you declare is that, yeah, you compile to Sierra as before your smart contract, but now you also compile from Sierra to the Cairo assembly, to the bytecode for the Cairo VM, right? You create a transaction, and the transaction will include, when you declare it, the Sierra code as before, but also the hash of the Cairo assembly. So when it goes to the mempool, and it's now the compilation from Sierra to Kazan done by the sequencer, it's easy to verify that this hash should be the same as the hash of the compile code from the sequencer point of view, right? So that's how we close this loop, this gap that we have right now by not having the Cairo compiler in Cairo. Now, declaring and deploying are two different actions on a Starknet. So declaring a smart contract, it only registers its code on a Starknet, right? So you only declare new code once. If the code is already declared, you don't have to redeclare again. So a declared smart contract is known as a contract class. And you're going to see there's some similarities with how OOP works, or object-oriented programming, in the sense that, okay, this contract class is going to be a blueprint to derive smart contract instances. Now, a contract class is identified by its class hash. Contract classes are pure code. They don't have internal storage. It's just the blueprint. They're not meant to be used directly or to be invoked in transactions. Now, when you want to deploy an instance of the smart or the contract class, what you will do is that actually you derive it from the contract class, you execute the constructor, and now you get the instance, which is actually the smart contract we normally refer to, the thing that you interact with, the thing that actually have storage internally, right? And this contract instance is identified by its address. So from the same contract class or the same code, you can derive multiple instances by deploying the instances, calling the constructor, and just they're all going to have different addresses, even though they're all derived from the same class, but the storage will be different. Now, the deployment, and this is part of the account abstraction model, is done through a system called the universal deployer. A universal deployer is basically a smart contract whose function is to deploy other smart contracts. If you're familiar with the ERC 4337 on Ethereum, you will see also the universal deployer there as well. That smart contract has only one function called deploy contract. And when you call this deploy contract, and again, this happens under the hood with your wallet, you don't have to care about that directly, but just letting you know that it exists and this is how it works under the hood. You will call this method, and you will have to pass to the method which class hash you want to use, right? Or which blueprint you want to use, and the arguments of the construction. Right? Because if I mentioned to create an instance, you have to define, okay, from which contract class, identified by the class hash, and you have to call the constructor, you have to execute the constructor. So you have to pass the arguments for this function. So internally, this universal deployer uses a syscall called the deploy syscall that's going to take these arguments and actually going to do the deployment of the instance. This universal deployer exists as a public good. It was created by Open Zeppelin. And right now it's written in Cairo 0. It will be eventually updated to Cairo 1. So there's only need to be one that we all use the same. Now, to compare smart contract classes versus instances, I mentioned that when you declare, using the declare transaction, what you do is you register new code or a smart contract class. When you want to deploy an instance from this smart contract class, you send an invoke transaction to the universal deployer, which is a smart contract that internally calls the deploy syscall. It will use this as a blueprint, passing the arguments of the constructor. It's going to execute it, and it's going to derive the new instance of the smart contract that's going to have its own address. And that is actually the smart contract that we normally interact with. Now, there's another use case for smart contract classes, and those are reusable libraries. In this case, you can, you declare the smart contract class, but now the way you can use it is that you can use the invoke transaction or just a call, and you can call the smart contract, at least the logic, because it doesn't have storage, only has logic, as a library call, right? So this way you can use reusable libraries on Starknet because you only care about the logic, you don't care about the internal state. When you use a library called syscall, you call the logic, but in the context of the state of the smart contract that is calling it. You're going to see that on Ethereum, you have similar patterns. And just here, the two ways that you can use smart contract as a blueprint for new instances or as a reusable library. So now, after you declare the smart contract, you can actually do the deployment. And of course, it'll start with your wallet. You will send an invoke transaction to Starknet. And in there, you have to define three things. And this happens, the wallet takes care of that normally, right? You have to provide the address of the universal deployer, which is a smart contract itself. You have to define the class hash of the smart contract, the class or the blueprint, and the arguments of the constructor. So now when it gets executed, the constructor of that class hash or the smart contract class gets executed in the Cairo VM, and that's how the new instance is created. That trace is sent to the prover, and the prover sends the validated proof to Starknet, and also it gives you, okay, the address of your deploy instance is this, right? That's how you will know. Maybe if you go to Starkscan, it will be easy to find that smart contract. Where do we see it? Sorry, that's not Starkscan. Starkscan, if I go to top contracts, maybe? No, address book, universal deployer, here it is. This is the public good that we all use to deploy smart contract. If I see, it's written in Cairo 0. It's not modern Cairo, it's old Cairo, but it still works. And if we see the code, you're going to see that there is a deploy contract function. This is all Cairo. This is not how it looks like, but just so you know that it is a smart contract. And look, it expects the class hash, and it expects the call data for the constructor, right? And what gives you back is the address of where your instance is deployed. We all use the same smart contract. We all call the same deploy contract. And normally this is done by the wallet itself, just for you to be aware that this is how it works under the hood. Now that your smart contract is actually deployed, you can actually interact with it using a different type of transaction called the invoke transaction. And in here, you define the address of the smart contract you want to interact with. You define which method you want to call, which selector, and you pass the arguments of that selector or that function. It will go to the mempool. The function will get executed here in the same. The trace sent to the prover, validated proof settled to Ethereum. and then you will get also the results out of the Starknet. This is a high level, how it looks like. We're going to go more into detail tomorrow. So to summarize this section, Architecture 101, Cairo compiles to Sierra. Sierra compiles to safe Cairo assembly. So this is its intermediate language between Cairo and the Cairo bytecode or the Cairo assembly. When you declare a smart contract, you create a contract class, and contract instances are derived from contract classes, right? So this is like an OOP model. From a contract class, you can derive multiple instances, which are the smart contract identified by address. A contract class can be used as a library. I mentioned there are two ways to use it, as a blueprint or as a reusable library. The Cairo assembly hash is used to prove compilation, and this is a stopgap solution to the fact that the Cairo compiler is written in Rust, not in Cairo. And deploying a new contract requires using the universal deployer smart contract that I just showed you. And we saw two types of transaction, the declare transaction and the invoke transaction. Congratulations, you made it to the end of the talk. By now you should have a high-level notion of how Starknet works and what makes it special. This talk is just a subset of all the information we normally cover on a bootcamp called Basecamp. If you want to learn more about Starknet and Cairo, head over to the Starknet Foundation YouTube channel and find the Basecamp playlist so you can watch 5 more sessions like this one with more in-depth content. Starknet is the ecosystem where the learning never ends. I hope you enjoy the journey.